The radical, fundamental principles of freedom, rational self-interest, and individual rights. This is the Yaron Brook Show.
All right, everybody. Welcome to Yaron Brook Show on this Monday, May 20th, second show today. I am particularly pleased today to have with me Keith Lockitch from the Ayn Rand Institute, a colleague of mine from way back. And I don't know what your formal title is at the Institute.
I'm the Vice President of Education.
Vice President of Education.
And a
Keith,
senior fellow.
And senior fellow, and he teaches at the Ayn Rand University. We'll talk a bunch about the Ayn Rand University and what he teaches there. I think it's really fascinating. Those of you who might have attended OCON last time, you did like a couple of classes, or you went through a portion of the course that you teach.
Yeah, I did sort of a mini course version. Basically, I went through the first couple of classes, and I can say, what I do in those classes, but it's like the introductory material that sets up the whole rest of the course. And I did that at OCON, partly as a way of advertising the course. And I think I got some people auditing the course because they liked the first part. So
good. So Keith is a PhD in physics, and from what, 25 years ago? It's been a long time.
Yeah, 25 exactly, almost.
Yeah.
So it was in relativistic astrophysics. I was in general relativity and related things.
All right. So general relativity, we might actually have a guest on who knows something about general relativity. So we'll find out, I guess.
Yeah, we'll find out, yeah. Because
I have no clue. So I used to know what that meant. I don't even know that anymore, but I never understood it. Good. So let's jump in. Of course, you guys can ask questions on the super chat. You can ask questions about anything really, but target them at Keith, not at me. So ask about ALU, about the university, about what we're doing at the institute. You can ask questions on physics, but make them useful, I guess. We'll talk about that, kind of useful questions in physics versus not so useful questions in physics. And yeah, I mean, basically ask what you want, but as you do anyway, you don't follow my advice. Let's see. Yeah, I think that's all we have. So tell us about the course that you're doing, that you're teaching. And are you teaching the same thing this year as last year, or is this year like part two?
Yeah, no. So this is I'm teaching. So the course is called The Foundations of Physical Science, Motion and Gravitation. And it's the second time I'm teaching the same material. So I'm kind of going through the material again. My goal is to kind of get a good recorded version, and then we can offer the recorded version. I may have to do it a third time, not quite there yet, but it's getting pretty good. So basically the idea is to talk about how we developed our understanding of the laws of motion and gravitation. So it starts from sort of, pre-science and ancient astronomy, just the very first observations that you make looking up at the sky. And we go step by step all the way up through basically Isaac Newton, through the laws of motion and gravitation. So that's what it covers.
Now, a lot of the observations, or the conclusions from the observations made when looking at the skies were wrong. So what's the value of studying them, of taking a class and going over all the mistakes that the Greeks made?
Well, okay, so let me say a little bit about my approach to the course, because I'm not, so if it were, the course is unique in a certain way. It's not, it's looking at the history of physics from a certain perspective and for a certain purpose. So you can take a course in the history of science, and if that's the focus, you'll cover all the blind alleys and all the false starts, all the mistakes that people made. But that's not my goal in the course. My goal isn't to teach the history of science.
Mm-hmm.
It's also not to do like a whole survey that you would get in an introductory physics course where you cover all the topics that you get in the first year. It's very narrowly focused on getting up to the laws of motion and gravitation. And really the goal of the course is there's sort of a meta purpose to the course, which is to show how human knowledge gets built up from perceptual observation. So, we do cover some of the ideas that people came up with in ancient Greece, so it's important to go through them, because even if some of them we look back and we know today that they're not correct, they were natural and plausible in the context of knowledge that they had, and you couldn't have gone to the next step without them. So we cover the steps that were essential steps in the development of human knowledge, not just covering errors for the sake of covering errors.
So, so how would you say this course is different from what some other people might have had in high school or even in college in terms of their basic physics or intro to physics or just physics classes?
Yeah, well, so I mean, the essential difference is that I'm proceeding hierarchically. So, what one of the major problems that we have today in education, but just in the culture in general, is the principle of hierarchy, which is sort of a principle of the objectivist epistemology. It's not understood at all. And what you get is basically what the principle comes down to is that there's a certain order to knowledge, that knowledge builds up step by step from perceptual observation. And if you try to introduce an item of knowledge that's very abstract without giving all of the context that gave rise to it, what the student gets is what we call just sort of floating abstractions. It doesn't really have any meaning for them, So what you'll get in a typical high school physics course, they'll just sort of introduce the law of gravity. You can write down the equation, masses attract each other, and there's a certain amount, it depends, it's proportional to the masses, inversely proportional to the distance, square the distance between them. They'll just give you Newton's law of gravitation without setting any context, without explaining how we came to know that, without any background. And I mean, one problem with it is the kids throw up their hands and say, why do we need to know this? Like, who cares? Right? Who cares how objects attract each other? So there's a motivation problem, but also they have no way of knowing, if you want to understand how we know that gravitation is this universal force that holds the solar system together. I mean, that comes from making observations of what we see, the stars and the planets that we see in the sky. If you send a kid out, on a clear night and they look up and they see these bright points of light in the sky. If you ask a kid who's taken a physics class in high school, like, how do we get from that to understanding this law of universal gravitation? They have no clue. And the teacher probably doesn't have a clue either, because they never learned it that way. So the point is, in order for it to truly be knowledge, instead of just being something, a factoid that your teacher has told you that you've learned from an authority figure, in order for it to have a firsthand understanding of it, you have to see how that law was built up step by step from observation, from the facts, from the perceptual observations that gave rise to it.
So maybe explain a little bit what hierarchy is as an objectivist epistemological principle.
Yeah, so it's the idea that there's an order to learning, there's an order to acquiring knowledge. Now, it's not, so just to clarify, it's not a metaphysical principle in the sense that reality is the way it is. And, the fact that, like, we know with special relativity, when things move very close to the speed of light, weird stuff happens. That was true 10,000 years ago, before people even knew there were such things as planets. That was as true then as it is today. There are things that are facts of reality that we haven't even discovered yet. And they're part of reality. They're out there. We just don't know anything about them yet. So reality does not have any sort of hierarchical structure. It is what it is. Okay. the hierarchy is an epistemological principle. It has to do with how we come to know things, and it has very important implications for how we teach things, how we, if you want to convey knowledge to a student, it has very important implications for that. And the idea basically is that there's a certain structure to our knowledge. Things build up in a certain order, and there's knowledge that's more abstract and knowledge that's less abstract. I mean, one thing that's sort of radical about the objectivist epistemology is the fact that, I mean, it holds that all of our knowledge, literally every item of knowledge that we have, has to be ultimately grounded in sense perception. So, and I say this is radical, but like in terms of the history of philosophy, this is a radical view because it rejects the whole line of, Platonic philosophy that says there's this abstract dimension or world of forms. We somehow commune with this, we get knowledge that's sort of intrinsic in reality that comes from this world of forms. I mean, you ask most mathematicians today, where does math come from? And they'll give you some version of Platonism,
Yep.
So the idea that all of our knowledge has to be grounded in sense perception is actually a pretty radical view, even though it seems like it should be kind of obvious, right? Yeah. So,
And that any abstraction is abstraction of what we observe through our senses.
yeah. So, so in the course, I mean, what I do initially is I take people through a whole discussion of like, what do you actually see if you systematically observe the night sky, or you like, what do you actually see? And I mean, obviously we can't go outside and do this in real time, so I use astronomy visualization apps and things like that, and images. But I mean, like literally the first fact that I bring up in the class is the fact that the sun rises in the east and moves across the sky and sets in the west. Like that's the starting point, for the course. It's like that kind of basic perceptual observation. And then, yeah, and so
from there,
so all of our knowledge builds up step by step from there. I mean, let me just give you an example. So, like we all know that the Earth is a planet, right? That orbits the sun, right? But how do we even know, like, we all know that in quotes, right? But so the question is, how do we even know that there are such things as planets? Like, if you had to point at the sky and say what are the facts of reality that actually gave rise to the concept of planet in the first place, like most people couldn't do that. But that's one of the things we talk about in the course as we go through. So this is what the ancient Babylonians and the ancient Greeks actually observed in the sky that led them to say, oh, we need a new concept here to designate some of these stars that move in a little bit of a different way from these other stars, and these, and so we call them planets.
Yeah. No, that's cool. That's cool because people want to talk about quantum mechanics and general theory of relativity, but yes, they probably couldn't actually lay out a proof that we are a planet, or what a planet is even, and what's required to know that.
Yeah.
I read it in a book, basically. I mean, I haven't been to space. I haven't seen it. That's how so much of our knowledge, unfortunately, comes to us, because that's how we're educated.
Yeah. And I mean, with quantum mechanics and relativity, there was a whole series of experimental observations and discoveries that led Einstein to develop these theories. He didn't just make them up in his living room, even like even there's a hierarchy of knowledge, and it's really I mean, it's fascinating. Like, it's fascinating, the history itself, but also you can't really understand what the theory is about without understanding the observations and the experiments and the whole context of knowledge that gave rise to his discovery. I have you asked whether this was a new course or was a repetition of the first course that I gave.
Yeah.
So I'm teaching the same material again, but I have this dream. I have this whole series of courses that I'd like to give. And the next one would cover sort of, electricity and magnetism and light.
Okay.
And then that would bring us up to sort of the 19th century, end of the 19th century, with Maxwell, who formulated the laws of electricity and magnetism and showed that light is an electromagnetic wave, which is this huge integration of optics with electricity and magnetism. And then after that course, I think the students would have the context I think I'd like to do like a special relativity and kind of do a hand wavy introduction to general relativity. So someday I'll get there, hopefully.
Would you include quantum in that?
Well, that would be different.
The quantum experiments are super interesting, right?
Yeah, so that would be the next. So I have this whole series in mind. So
Okay.
then what I would have to do is go back and talk about the history of chemistry and the atomic theory. So you'd have to go like it all starts back in ancient Greece. So we'd start
Electromagnetism leads to Einstein, and atomic theory leads to quantum.
roughly. I mean,
Interesting.
by the end of the
I didn't know
19th
that.
century, they're all sort of interrelated.
Yeah. Yeah.
But in terms of structuring a series of courses, you can do light, electricity, and magnetism, then relativity, and then you could do sort of chemistry and the history of the atomic theory, which again,
Goes back to
actually,
Greece.
again, it culminates in Maxwell. Maxwell was as much of a genius as Newton. He's like one of the greatest physicists of all time. So he was seminal in electricity and magnetism, and also in atomic physics, statistical physics. And then after that one, you could do quantum theory, nuclear physics, all that good stuff.
All right. So a lot to look forward to. I mean, you're still young, so why not?
Yeah.
I don't know. It seems like a plan to me. You can't. I don't know that you can do them 3 times every single one of them. So you'll have to get more efficient at getting it down in maybe 2.
Yeah. I mean, I'll circle back and cover some of them again. So
yeah, good. No, that sounds like so. Why are we teaching physics at Ayn Rand University? I mean, it shouldn't we be just teaching philosophy or humanities? Why should some of these students who are more interested in philosophy be taking a physics class?
Yeah. So there's 2 parts to answering that question. One is, so our sort of training program, our educational program, when we used to call it the Objectivist Academic Center, and it was much more narrowly focused on objectivism, on topics in philosophy. We would cover objective communication. It was basically, the idea was it was intended for people who were interested in an intellectual career. And so it was sort of trying to give the essentials of what somebody needs to work as a professional objectivist intellectual. They need to know the philosophy, they need to be able to think philosophically, and they need to have communication skills. So we had courses on writing and speaking and all that.
Yep.
What we've done in the last couple of years is we've really expanded the curriculum to encompass other fields with the goal of, so the not every ARU student, we don't think of them necessarily as somebody who is going to become a professional intellectual, but it's somebody who wants to really understand objectivism and to use it as a foundation for life, to build it in as part of the way, as their framework for the way they think about the world. And so partly in terms of in thinking about the shift in who we're trying to reach with the program, we wanted to expand the topics that we cover because, understanding how objectivism applies to literature, to psychology, to economics, to finance, to physics, like it has, objectivism is such a radical, original set of ideas. It's sort of such an original philosophy. It has huge implications for all these fields. And so we wanted to expand the curriculum to include, some instruction on how to think about these different fields using objectivism as your framework. Now, with the physics courses in particular, the second part of the answer is it's partly has to do with what we talked about the way the course is being taught. Because the course proceeds in this hierarchical step-by-step fashion, the idea is, as we said, like you take a group of people who've grown up in today's culture and you say, well, how do we know that there are such things as planets? Well, they don't know that, right? So, and they know they don't know that. So the idea is, what I want to do is I want to take them step by step through the process of understanding in a first-handed way how we know these kinds of things. And the goal is for them to have an understanding of what that looks like, what the difference is between being told that something is true versus actually being able to see that it's true for yourself, all the way down to perceptual reality. And having a grasp of that difference is so important. And so that in terms of it's so important for your own objectivity to be able to know that you know something, and then to be able to contrast that with things that, oh, I actually, now that I know what it looks like to really know, understand the solar system, now when somebody says something, tells me some other thing in science, well, I don't actually know it like that. Like, you've got to, it really concretizes what it feels like and what it looks like to have a firsthand understanding, as opposed to just being told, yeah, the Earth is a planet, it goes around the sun, spins on its axis. So that's
just an objectivity in terms of what you know and what you don't know, and improves your ability to detect your own ignorance.
Yeah, and then when people go on, so this is a first level course. When people go on to study objectivism at a more advanced level and they start studying epistemology, they start learning more about what objectivism's view of the nature of knowledge. Having examples like this from the history of science is really helpful in terms of concretizing ideas about epistemology.
To what extent are you modeling kind of the inductive method?
Yeah, I mean, so I describe it as a hierarchical approach because I think that's actually broader. Not every step in the logical development, from looking up at the sky to the laws of motion and gravitation, is an inductive step. But there are a lot of inductive steps that happen along the way. And so examples of induction come up, throughout the course. I mean, just to give an example, that we talked about how we know there are such things as planets. So once you have the concept of a planet, then you can, well, one of the interesting points that comes out in Leonard Peikoff's theory of induction is the idea that, in a nutshell, sort of the basic problem of induction is, how do you justify going from some to all? How do you justify generalizing? And one of the really interesting things that comes out of his theory is that Ayn Rand's theory of concepts shows us how we go from some to all, because that's what a concept is. You form a concept on the basis of a limited number of perceptual observations, but once you form the concept and have the unit perspective on those things, it stands for an unlimited number of units, right? So the process of concept formation itself represents the passage from some to all. It represents that phenomenon of generalization. So so if you have the concept of planet and you discover something about one that's true about one planet, qua planet, you know that it's true of all planets, for instance.
So let's talk a little bit about the Ayn Rand University. Tell us a little bit about, beyond the course, what are the goals of the university? What's the goal of the program? I mean, one obviously is we want to train future intellectuals, but we're not just attracting future intellectuals. This is pretty open and to anybody to come and join. So what's the goal? What's the purpose?
Well, so the Ayn Rand University itself is aimed at anybody who really is interested in understanding objectivism as a level that they can use it as the framework for their life. And we have some new developments that I think I'm not supposed to talk about yet. They're going to be, where the Ocon is
Announced
coming
at
up.
Ocon, I'm sure.
Yeah, announced at Ocon.
Fanfare. Yeah.
Yeah. So, but the idea is ultimately our goal with the program is to scale it up as much as we can to reach as many people as we can. I mean, we would love, right now we have, 100, 150 people taking courses with us. If we could 10x that, we're trying to scale up as much as we can to maximize the impact that we can have on people. And I'm talking about people studying it at a deep level to the point where they can make it the framework for their life.
Mm-hmm.
Obviously for us, from ARI's perspective, what we're also trying to do is use ARU as a recruiting ground for potential future intellectuals. So we're evaluating the students, looking at their potential and their interest in an intellectual career. And so on top of Ayn Rand University itself, we have the ARU Graduate Center, and that's our sort of training program for future intellectuals. And so they're different programs though. When I think back in the days of the OAC, there was sort of one program, and it was intended. There was a way in which it was a little bit at cross purposes. It was, for people who wanted to learn objectivism, but also for future intellectuals. Now we've separated them, and they're much more focused.
Mm-hmm. And tell us a little bit about what other courses are being taught, what are being taught at the ARU, and is the methodology the same? To what extent is objectivism run through all the courses that are being taught?
Okay, so the first part is, the core obviously is still objectivism. So when people come into the program, one of the first courses they take is a course called Objectivism Through Ayn Rand's Fiction. And the idea is that, the Ayn Rand's novels are obviously they're meant to be read as works of art, as an end in themselves, but they're also extremely rich philosophically, and I think in ways that people don't always fully recognize just how much, she developed her philosophy in order to write the novels. And there's so much richness and philosophical depth just in the novels themselves. I think sometimes people have the impression that, yeah, you read the novels and you put them aside and you go on to the nonfiction. That's where the real philosophy is. And that is far from the truth. So the first course is an in-depth study of the novels and the philosophical ideas in the novels. And then we also have a second year objectivism seminar, which is a detailed study of Objectivism and the Philosophy of Ayn Rand by Leonard Peikoff, where you really, you study the philosophy in depth. We also have, and then we have, as I said, we have courses on covering other fields. So in literature, we have a course that's based on Leonard Peikoff's lecture course, 8 Great Plays. So he has a lecture course where he selected 8 sort of monumental plays from world history, where the students read the play and they're recorded lectures from Dr. Peikoff on that, and then they do assignments, and we have instructors who lead discussion sessions, and so we've made that into a course. We have my course on the foundations of physical science. We have an introduction to psychology that Gina Gorlin is teaching right now. We have a course called Philosophy, Work, and Business, which is thinking about your career and work and business and productivity, and how does that fit into a rational life. So a whole variety of offerings touching on different fields. Shoshana Milgram has done a couple courses on literature for us. She did Dostoevsky's Crime and Punishment last year. This year she's doing Hugo's The Man Who Laughs. And they all you asked if they're all if they all bring objectivism in. I think depending on the subject, they do it to a greater or lesser extent. The courses on objectivism obviously are all about objectivism, and with my course, it's not explicitly philosophical all the time, though. The objectivism comes in that the whole course is designed using objectivism as a framework and in thinking about the order of learning and how to present the ideas. So yeah.
So it's modeling objectivist epistemology in a sense. How to think.
I like to think so. Yeah. Yeah.
All right. So we have a ton of questions.
Okay.
I don't know. We've got 20 plus questions.
Let me before we go into the questions, can I just say one prefatory comment, which is that I stopped doing physics, like more than 20 years ago. So I'll try to answer them as best as I can, but I may have to punt and
All right. So with that, all right, I need to remember to look over there, but most of the questions are here. Do you agree with George? This is from Chris. Do you agree with George Box's quote, all models are wrong, some are useful? More broadly, how do you see the role of statistical modeling in understanding reality?
Okay, so there's two parts to that question. I do not agree with that quote because it encompasses a certain kind of skepticism about knowledge that's very typical today.
Pragmatism, right? Is it useful?
Well,
there's
a pragmatism, but the idea that all models are wrong. We can't actually know anything about reality.
Yeah.
Maybe we can find some useful models. So if a model is an attempt, like a proper model is an attempt to capture some sort of causal aspect of reality. And to the extent that it does that, a model can be correct, Now, as far as the role of, what was the second part? The role of
statistic modeling in understanding reality.
Yeah. I mean, I don't know that much about how statistical modeling is done today, but it's like it can definitely be abused. We all know the principle that correlation doesn't equal causation, but I think if it's used judiciously, you can uncover you can uncover truths about the world through data analysis methods and statistical methods for sure. But
half of finance today is statistical modeling.
Yeah.
Don't have a field of finance of investing without statistical modeling.
Yeah. But it can definitely be abused, and you see, you see all kinds of problems, in the scientific literature today. They talk about things like what they call p hacking, like people just trying to publish papers and they'll massage the data to the point where they get a statistically significant result so they can publish the paper, but it actually doesn't mean anything or give us any insight into what's happening in the world. So it can definitely be abused, and one has to use it judiciously.
Yes, I mean, generally statistics are tricky. I mean, and hard and non-intuitive often, and people abuse them all the time.
Yeah, I mean, there's a famous book called How to Lie with Statistics.
Right? Yeah, and people do it all the time. And you saw that probably more than anywhere. You saw that in the COVID debates on both sides of whatever argument there was. Both of them were just distorting statistics left and right. It was, and most of them didn't even know they were distorting the statistics, right? They really believed them. It takes knowledge to know you're ignorant.
Yeah.
Right. All right. Let's see. Blackout asks, was the advent of man the advent of self-initiated action as opposed to billiard ball style reaction? If so, would this not imply that the origin of action stretches back to an infinite series of predetermined reactions?
I mean, I think what that question is getting at really is the question of free will and sort of what is the, evolutionary biological origin of free will. If I understand, I think that's kind of what it's getting at. And, you know, so I don't think the implication is that there's an infinite regress of billiard ball style causation leading up to somehow the advent of free will. Like there's a way in which if I'm understanding the question correctly, it sounds like there's an implication that there's a certain contradiction. Like you have billiard ball style causation all throughout, the history of the universe, and then somehow magically self-initiated action arises out of that. And how is that possible?
Mhm.
And I mean, it comes down to the question of what is the sort of physical basis of free will. And that, I mean, the mind body problem. And that is something that I don't think we know the answer to, as a matter of, physics and neuroscience and so on. However, it's you don't need to have an answer to that question to know that there is such a thing as free will. And objectivism, objectivism as a whole has a whole set of arguments as to how volition is axiomatic and all that sort of thing. And, you can look at that up in the literature.
And objectivism does not, first of all, we don't know that the advent of self-initiated action, man is the first being in the universe to have free will. We don't know that. We know we have it, but we don't know more than that.
I mean, we don't have any evidence of any other beings that have free will, so we can say that at least.
Sure, but Rand was pretty careful not to, I think, attribute. And then, we don't also see causation as billiard ball, right? I mean, the essential nature of causation is not the billiard ball. And I don't know how quantum mechanics fits into billiard ball causation, right? It doesn't seem like that simplistic model really explains parts of reality.
Yeah. I mean, that's the important point when it comes to causation is causation is about the action of entities, not about
and the nature of entities.
Events happen, the order of events or one event bringing about another event. It's about what is the identity of an entity, and that gives rise to the kinds of actions that are possible to it.
Yep. So with regard to free will, Clark asks, we'll see if you contradict me in this one. Yaron always equates free will with gravity, arguing that we don't know what explains either, but both are observable. Don't we understand gravity as the presence of mass creating waves on the fabric of the space-time continuum?
Yes, that's exactly what it is. Really? Well, I mean, in a rough, non-technical sense. I mean, so Einstein has a very different conception of gravity from Newton's conception of gravity.
Mm-hmm.
For Newton, for some reason, masses have this attractive force with each other, right? That operates, according to Newton's law of gravitation. Well, see, yeah. Now I'm finding myself in a position of I'm wanting to start to explain, Einstein's theory of gravity, but I think in the act of doing that, I would violate everything I just said about the principle of
hierarchy. Yeah.
So all I could say is when I give my course on relativity theory, sign up for that, and I'll sort of take you through the ideas.
I will. All right. Yeah. I'll sign up. But I think my point is that we still knew gravity existed before Einstein had a theory.
Oh, yeah.
We knew this, right? So the point is, gravity was observable for millennia. I mean, it's always to human beings. They understood something was going on. They didn't reject it because they didn't have a physical explanation for it. And my point about free will is it's observable. We know it's happening.
Oh yeah.
We can't reject it because we don't have a physical explanation for it. So
that I agree with
maybe we have a
completely.
physical explanation for gravity, and maybe one day we'll have a physical explanation for free will.
I mean, they had the concept of gravity back in ancient Greece. You know,
Yeah.
I mean, they had, Aristotle's explanation for, the spherical shape of the Earth, in effect, is all matter is seeking its natural place at the center of the universe, and that's whatever direction you're coming from. There's a way in which that is an attempt to understand the phenomenon of gravity. And Archimedes, had the concept of a center of gravity. So we could talk about,
Oh, yeah.
we could talk about bodies floating in water and would they stay upright or would they flip over, and the whole law of the lever is the concept of center of gravity. So, people were thinking about the phenomena that we now understand as gravitational attraction for thousands of years before Newton formulated his law of gravity. So yeah, so that I agree with completely. The facts are undeniable, and I think it gets back to the point that I made earlier in the conversation, which is reality is the way it is.
Yeah.
Even if we haven't yet figured it out, or we haven't yet built up our knowledge to the point where we fully understand a particular phenomenon. So there are all kinds of things that we don't yet understand about the physical basis for free will. How it is that, our consciousness is embedded in this physical brain and so on. And people, I think one of the consequences of people not fully understanding or embracing this principle of hierarchy is that they almost feel like we have to have an explanation. We have to try to answer the question, even if we're missing huge pieces of, we don't have any way of knowing what the answer is now, but we have to still somehow come up with an answer. Well, no, you don't. You can say we don't know yet, and that's completely legitimate, but we know there's free will, because for all the reasons and the arguments that you get in the objectivist literature.
So related to that, there's this theory, I guess, by Stuart Hameroff and Roger Penrose, that consciousness and free will are supported by quantum physics. That is, you can explain them through quantum physics, and supposedly they've done experiments to prove this, that free will is a phenomena of quantum mechanics.
So I'm not familiar.
Thoughts on that?
Well, I'm not familiar with the theory. I'm not familiar with the arguments, but it seems plausible to me that so on the one hand, yeah, it like it. I mean, we know that reality, that the physical world at the subatomic scale obeys quantum laws. So if you're trying, so whatever explanation you come up with for how the brain works and how, anything related to consciousness, it ultimately has to be consistent with quantum physics. So if they think they've come up with a theory that is plausible, the only thing that gives me pause is I'd like to know what their conception of free will is, though, because objectivism's conception of free will is very distinctive.
Yep.
And very original, and it's not one that you typically see when people talk about free will. So that's my only
if they can come up with a physical explanation of consciousness, that would be huge, right? Because we don't know animals are conscious, even if they don't have free will.
Right.
That doesn't seem. How do you do that? From a physics perspective, how do you do that? It doesn't seem like it should be doable, and yet that's reality.
Yeah.
Right. So Michael asks, is it a widespread fallacy that everything must reduce to physics? what would it mean for something not to reduce to physics like free will or consciousness?
Yeah, I mean, I think it goes by the name of reductionism. That's uh, and so trying to I mean, I think the point is that trying to reduce everything to physical laws doesn't actually allow you to account for the richness and insight that you get from looking at the phenomena themselves.
Or would you say that every phenomena ultimately has its origin in physical laws?
Well, there was a book I was reading recently that discussed this issue and talked about it in a way that I agree with, but I'm not remembering the details of it right now. The point is that what does it mean to reduce it to physical laws? Like you lose a lot of the richness and the meaning of the idea itself when you try to say that in some sense you can derive it or reduce it to physical laws. That's not a great answer, but that's the best I can do right now. But I mean the short version is I think yes, that reductionism is not the right approach.
Adam says, Keith, I remember suggesting Zeilinger 1999 foundational principles for quantum mechanics. Zeilinger writes, despite his personal preferences for Copenhagen, that the FP is compatible with inter alia, the Bohm interpretation. Did you read it?
I remember we had a session about this, but this is where I have to say that I've forgotten more things about physics than most people ever learn, and so I think I did read the paper, but I would have to I'd have to do a lot of work to just refresh my context to be able to talk meaningfully about that.
Shazbot says, how long before humans can build a Dyson Sphere?
My son is always asking about this because he watches these videos from Kurzgesagt, which are they have these little science animation videos.
Okay.
And so he's always going on about Dyson spheres.
So what's a Dyson Sphere? I
So
don't know.
a Dyson sphere it's a method of extracting energy from a black hole, from a spinning black hole. And just like you have to, but so first of all, you have to get to a black hole. You have to construct this structure that surrounds the entire thing in order to do it. So, I don't I can't even predict when we're going to get to Mars, even though some people think they can predict that. So I don't know when we're going to be able to build a Dyson sphere. Someday, assuming we don't
Getting a
destroy
black
ourselves.
hole means we have to be able to travel faster than the speed of light.
Well, you could just have to get close enough to the speed of light that the distance between us and the black hole gets short enough, and you can get there in a human lifetime.
Really? Is a black hole that's that close?
I mean, there's a black hole at the center of our there's a black hole at the center of every galaxy, basically.
Okay.
Yeah, they're all over the place.
So Shazbot, once you figure out how to travel close to the speed of light within one lifetime, that's the best answer we have. And then you have to build the thing. So yeah, I don't know.
Put Elon Musk on the problem. He doesn't have enough that he's working on right now.
That's right. All right, Daniel, forgive me. I'm publicly educated and have an embarrassingly dearth understanding of hard sciences. Any good resources to help me as an adult? I assume you'll plug ARU, but perhaps you can include other resources too.
Well,
Maybe these animated.
Well, no, no. So the animated videos are exactly the problem of violating hierarchy. My son's talking about Dyson spheres and he has no idea about anything in physics. So that's the whole problem right there. And
Yep.
Kurzgesagt means in a nutshell, and that's perfect because that's the whole problem in a nutshell.
Yep.
You know, it's hard to recommend any kind of general resource. If there's a particular area of the history of science you're interested, I could recommend resources on that. But just, you know, I would, as you said, I would recommend taking my course if you want to understand the things I was talking about there. You know, I mean, the book that's based on Leonard Peikoff's theory of induction, The Logical Leap by David Harriman, that's definitely worth reading. And it talks about, so it presents Leonard Peikoff's theory of induction, but it's concretized with examples from the history of science throughout. So that's really valuable. So that's one resource I would recommend.
Rafael says, hi, I know the universe is a finite plenum and does not exist apart from bodies. Asking what exists outside the universe is invalid, but can entities expand the finite space? If so, where are they expanding into?
Well, it's not that asking what exists outside the universe is invalid. It's that it's not the right way to conceptualize it. There is no such thing as outside the universe. So there is only the universe. That's what exists. And it has a certain, you know, spatial structure. And so if it expands, it's expanding. If it contracts, it's not like it's expanding into nothingness or something like that. That whole way of thinking about it is not right.
But it seems like the only way to think about it. How do you think about it and not think that if it's expanding into something?
You have to get away. So the problem is, here's the way people think about the universe.
Mm-hmm.
They think we're sitting here on Earth and there's a bunch of stars and planets and galaxies. And if we were to zoom away from them, we would go further and further out. And eventually we'd get far enough away that we're away from all the stuff that exists. And we're out here with some kind of God's eye view. But you can't think about it that way, because there is no such thing as zooming out. You know, wherever you are, you're in the universe.
Mm-hmm.
And to get from any place in the universe to anywhere else in the universe, you have to travel at a finite speed. And wherever you are, there you are. And, you know, so there is no God's eye. Like, you have to get away from the idea that we can have some kind of God's eye view on the universe.
And is that the answer to the shape of the universe?
Well, so I don't have a view that I would say I'm 100% certain of about the shape of the universe, but there are definitely ideas that I think are plausible. And so the way to think about it is, so you can have a geometric structure or a geometric object that is both finite but unbounded. Okay, so in one dimension, imagine a circle, like a ring. Okay, so let's say you're confined to one dimension, and you can go, you know, this way. You can go clockwise or counterclockwise. So you can always go a finite distance, but there's no limit on your ability to keep moving in either direction, right? Okay, so now take that to two dimensions and imagine like the surface of the Earth, a sphere. Okay, again, you can go all the way around from the North Pole to the South Pole and back, or you can go all the way around the equator. There's no limit. It's your motion is not bounded by anything. You don't reach an edge, but nevertheless, it has a finite surface area. Okay, so now you can imagine projecting that to three dimensions. And there are three-dimensional, you know, mathematically, you can define the three-dimensional equivalent of a sphere, where if you go off in one direction and you keep going long enough, you know, eventually you'll come around the other side. And if you go up in this direction, you'll come up here, and etc. Go this way, you'll come around, you know. So that's meant to just make the point that there are plausible ways to think about how the universe can be finite but nevertheless unbounded. And I think something like that probably has to be true. And this is, you know, so the question, this is sort of, what is the global topology of the universe? And I don't know the answer to that question, but I think something like this has to be true because we know, because, you know, one thing we know that's not true is that it's not, you know, again, when we think about this God's eye view, we imagine, you know, the sort of Cartesian coordinate system and, you know, X, Y, Z going off to infinity in all directions.
Yeah.
Like that's just how we're trained to think about space. But that can't be right because, you know, we know that we know the universe is finite, just on metaphysical grounds.
Yep. Raphael, I think, says in the comments, he says, can't get my head around this. Need to think more about it. And I would just say, I guess I'd ask that question, why? But because, yeah, I mean, you can spend a lot of time thinking about some of this stuff, and it's hard. It just is.
Yeah, but I think it's useful to really almost force yourself to say, like, this idea that I can zoom out.
Yeah.
I have to stop myself doing
You
that
have to
because
accept the metaphysical reality, and that's like that it has to be finite because that's metaphysically, and whatever the answer is ultimately to shape or whatever has to fit into the idea that it's finite.
yeah.
People
You
have a
know,
hard time with that. Yeah.
in the so the Leonard Peikoff has a lecture course called The Art of Thinking, and he made a point in there that really had an impact on me, which is it goes under the heading of volition as a means to clarity. He says if you you can get yourself into a situation where you convince yourself rationally that something is true, but you can't seem to shed the a wrong view that comes from an older context. And he says you can just use your free will to say to literally just like force yourself to say, look, I know this is wrong and I've got to stop thinking about it that way. Think about it the right way. And you know, you can change over time. Like, so I no longer I no longer am bothered by questions that people have asked, you know, from time immemorial, which is, you know, you throw the javelin to the end of the universe, what happens when it hits the edge? I'm not bothered by that because there is no edge and the javelin's never going to get there anyway. So,
Yep. All right. Daniel asks, can you break down? This is a good question, right? Can you break down quantum mechanics, Barney style, i.e., for the extreme novices? We don't know anything.
I mean, I'm tempted to say no, but
Well, partially
just,
because it contradicts the whole idea of hierarchy.
but let me say
You can
this.
jab at it anyway.
Yeah, no, let me say this. So there's there's a whole series, as I think I said this earlier, there's a whole series of observations and experiments that gave rise to the need for a whole completely different way of thinking about what the physical world is like at the atomic level. And we know that the sort of classical 19th century picture of the world, there are things that just cannot be right about it, like that, and that gave rise to, and let me just give an example of this. So when after it was discovered that, you know, so you know, after we were, you know, the atomic theory had been proved, so we know that matter is made of atoms, and it was discovered that atoms consist of a small dense nucleus with electrons sort of whizzing around them, right? Initially, people tried to kind of come up with a model of what the atom was like, thinking about it by analogy with the solar system. So you imagine, you know, you got the sun at the center and the planets are all whirling around it, held in their orbits by the gravitational force.
Mhm.
So people would say, well, maybe what an atom is you've got this dense, positively electrically charged nucleus, and you've got the electrons that are negatively charged. And so the electrical force holds them in orbits in the same way that the gravitational force holds the planets in the orbits. But the problem is that doesn't integrate with what we know about electromagnetism, because when the planets are orbiting around the sun, they're accelerating. The fact that they're moving in a circular orbit means they're constantly accelerating towards the sun. They're being pulled by the law of gravity. Well, if you have a model of the atom where the electron is being pulled towards the nucleus, and that's what keeps it orbiting around, you have a charged particle that's constantly undergoing acceleration. Now, the problem is that we know from the laws of electromagnetism that when you have a charged particle that undergoes acceleration, it's going to radiate away energy. So what would happen is if you actually had a system like this, the charged particle would orbit around, it would radiate away, and it would spiral in, eventually it would collapse into the nucleus. So people did this calculation, and they found that, if that were what atoms actually were, their lifetime would be like a matter of nanoseconds. So in other words, so you couldn't have matter wouldn't exist as we know it if that were the model of the atom. So it was only by coming up with a quantum model of the atom that people were able to, come up with a way of thinking about what atoms are that are actually, that are actually stable and that actually agree with experimental results that have been observed. So the point is, people were driven to, there was a need to come up with something like quantum mechanics. And I can just say briefly, the first answer that was given to this problem was Niels Bohr's model of the atom, which basically what he said was, in effect, the electrons are orbiting around, but they can't exist at any distance from the nucleus. They can only exist in certain quantized, so they can jump, but they can't spiral in. And so that, so that was the first sort of quantum model of the atom that people came up with. Now, the problem is we don't, at least, the solar system model is like a physical picture that we can understand, and it gives us, the attempt at a kind of causal understanding of what this thing is. We don't have any kind of causal understanding of what's going on when you have, when you have like these quantum jumps, so the problem is, the need for quantum mechanics was, arose, we were driven to it by experimental results and observations and things that we knew we needed something like that. And we have, a mathematical theory that can be used to predict the results of experiments to incredible accuracy. And I mean, the whole modern world, technology, our cell phones, none of it would exist if we didn't have quantum theory. But the problem is, what we don't have is any kind of physical causal understanding of what's going on.
And because the way I remember very vaguely quantum mechanics, there was this confusion about waves and particles and the differences between them, and was there a difference between them, or were they the same? Is that part of what quantum physics is? Was that just misconception?
So no, that's right. So what we find is that at the subatomic level, matter and energy seems to have both a wave-like character and a particle-like character. We know that I said earlier that James Clerk Maxwell proved that light is an electromagnetic wave. Okay, but a couple decades later, Planck proved that light has a particle-like nature to it, and Einstein also, proved
the photon.
The photon, exactly. And like we talked about electrons we think of as these little charged particles, but they also have a wave-like character to them, and they interact with each other in ways that waves interact with each other. So now I think often the way this is presented is that this is somehow contradictory. Like it either there's, I think, is a certain rationalistic kind of premise. Well, so things either have to be particles or they have to be waves. And what I would say is, no, what we're encountering here is a completely new phenomena, and we need a completely new way to conceptualize it and to think about it.
Yeah.
And we have to get to a causal understanding of the phenomena that we're talking about. And we can't assume that things have to be particles or have to be waves. We know, again, it's like we know, the same way we know we have free will, even if we don't fully understand it, we know that subatomic particles have both of these aspects to their nature. And, the job of a physicist should be to try to get to the point where we have some kind of causal physical understanding of it.
So I think in that context, do you think there is an ether, and why or why not? And he says ether doesn't have kinematic properties, but has other physical properties.
Well, so okay, so there's a few things to say. So I don't think that there's an ether in the 19th century sense of that's the sort of fluid that gives rise to electromagnetic waves. In the same way that you can have water waves, and when a water wave flies along, what it actually consists of is these water molecules in motion, right?
Yeah.
And people had the view that the same was true of electromagnetic. There's some substance, the luminiferous ether, and that substance was what was necessary to support electromagnetic waves. So I don't believe in the ether in that sense, but there's a way in which, just on metaphysical grounds, we know that there is no such thing as nothingness. Like, we know that there's no absolute vacuum. So in that respect, objectivism holds that the universe is full of something, right? Now, I think of the way the objectivist metaphysics conceives of the ether as it's sort of a metaphysical placeholder. We know that there's something there. And it's the job of physics to figure out what it is. And then the question is, what can physics say about that? My view is that so there's a lot that one could say about, from the point of view of quantum physics and quantum field theory about that. I think I tend to think that the gravitational field in general relativity is a plausible candidate for like something that could play the role of a physical ether. But I'd have to, in order to make that clear and support it, I have to give the whole course that I want to give on the subject. So
yeah. All right. Daniel asks, what is your opinion of the Big Bang Theory? He says, personally, I think it's BS.
Well, if
this is the same guy who said he knew nothing about science.
Oh, okay. Yeah,
but Daniel's a good guy, so I'm not making fun of him.
It depends. It depends what you mean by the theory. So if you think that if you take the theory to be claiming that the universe, came into existence out of nothing and then, blew up in the Big Bang, that's obviously wrong. So the universe is finite. The universe is eternal. In this sense, objectivism agrees with Parmenides back in ancient Greece, which is that what is, what is not, and cannot be. It's not the case that there was some point in time when nothing existed. Like, nothing doesn't exist. There is no nothing, and there can't be nothing, and there can't ever be nothing. But that's, so people, when people talk about cosmology and they talk about the Big Bang Theory, they often lump that together with the observational evidence that everything in the universe, has expanded from, some small dense point, and that the stars and galaxies are moving away at a certain rate, so I think all of that observational evidence, I don't have any reason to doubt that. I haven't spent a lot of time studying it, but you know, the idea that the universe expanded, you know, that it has this history that cosmologists describe, and then it expanded from a small dense state, whatever, 14 billion years ago. You know, now what was there before that? I don't know.
Yep. It had to be something.
Right.
Daniel Loss asks, what is your opinion on intelligent life on other planets?
It would be great to find intelligent life on Earth
Yeah.
first.
Give me intelligent life now. Anyway.
Yeah. Yeah. I mean, I don't, I think opinion is the right word, because there's no evidence one way or another that there is intelligent life somewhere else. There's a lot of probability arguments, you know, that there ought to be or there might be, but there's no positive evidence for it. So.
Oh, he asks, chemical reactions are said to be spontaneous and not or non-spontaneous if the products are lower energy than the reactants. What is the physical difference between a high energy molecule and a low energy molecule?
Well, that is a very specific question. I mean, it has to do with the binding energy of the molecule, I guess, you know. So
High energy would be a strong bond, or
yeah. I mean that's really a
chemical
physical
question.
chemistry question.
Yeah.
So yeah, that's something you could Google and look up the answer, and you'd get a better answer than what I would give you.
Yeah. Daniel asked, in movies, people that travel close to the speed of light age slower than others. I thought this was flawed because perception might slow, but biological processes are separate. Am I onto something or on something?
Well, those aren't mutually exclusive alternatives, so it could be both. But no, so these phenomena that come up in the context of special relativity, the so-called time dilation, length contraction, these are real phenomena if you understand them and you put them in their context. Okay, so and the problem is that it's very easy to draw mistaken conclusions that make you think that there are contradictions and paradoxes. In the history of special relativity, you know, years after Einstein published his theory, there were people who still were arguing, oh, it necessarily leads to all kinds of contradictions, which is not true. If you understand how it works, there's always a self-consistent perspective on these things. And I can give you an example. So this is something I did when I was an undergraduate. We did a lab experiment. Okay, this may take a few minutes, but let me go through it because it covers the essential ideas. So, basically the idea behind special relativity is that spatio-temporal relationships are affected by motion. So when you have bodies in a state of motion, the spatio-temporal relationships that you'll measure are different if you're in a state of motion close to the speed of light than if you were, you know, at rest with respect to the thing you're measuring. So an example of this that's often used in physics classes is so when you have there are cosmic rays flowing through intergalactic space, and when they slam into the upper atmosphere, they create particles called muons, which are like heavy electrons. Okay, and these muons will travel to the surface, will travel down towards the surface of the Earth. Now the problem is that the muon has a certain half-life. So what that means is if you've got a bunch of muons that they get created in the upper atmosphere, after a certain amount of time, half of them will have decayed into decay products. And then of the half that's left, you know, in the same amount of time, another half will be, so there'll be a quarter left, and so on. It's an exponential kind of thing. So So if you look at the speed, so these muons are moving very close to the speed of light when they get created in the upper atmosphere, and they're racing toward the surface of the Earth. Now, if you take the known muon half-life, okay, and the distance that they have to travel from the upper atmosphere to the surface of the Earth, it should not be the case that like almost all of them should have decayed before they get to the surface of the Earth, just taking the distance and the travel time, okay? But I actually did this experiment as an undergraduate in the lab. What you find is that, in fact, a significant number of muons make it to the surface of the Earth, and you can measure them in a measuring apparatus, and you can measure their half-life, and that's what we did in the experiment. Now, how is that possible? Well, it's because of the phenomenon of length contraction and time dilation. So if you're traveling with the muon at very close to the speed of light, okay, the distance that you would measure between the upper atmosphere and the surface of the Earth is shorter than the distance that I would measure if I'm standing on the Earth measuring the distance between the upper atmosphere and the surface. So because the distance that the muon has to travel is shorter, it can make it in the same half-life, it can make it, that where you would think that most of them would be gone, a significant number of them can actually make it to the surface of the Earth because of length contraction. So then you say, okay, well, how is that consistent with my perspective on the muon? Because I'm standing here on the surface of the Earth, I measure the full distance, and yet so how does the muon make it? Well, from my perspective, the muon is moving towards me at close to the speed of light. So when I measure the duration between events, that for an object that's moving close to the speed of light, you have the phenomenon of time dilation. So time sort of slows down. So the muon half-life is actually greater when it's moving close to the speed of light. So from my perspective, the muon undergoes time dilation and it can make it to the surface. From the muon's perspective, it measures its normal half-life.
Yep.
And there's length contraction, so it can make, so it's a self-consistent picture. And to bring it back to the question, if you were traveling towards me at close to the speed of light, and I were to measure your heart, let's say that I had some way of measuring your heartbeat, okay, you would measure you sitting on your spaceship traveling towards me, if you measure your heartbeat at 100 beats per second, you'd measure like a normal heart rate, right? But if I were somehow able to measure your heart rate, if you're going close to the speed of light, I would measure the heart rate to be, it would be much, much slower. Like literally biological processes, I would measure them to have slowed down from my rest frame looking at you moving close to the speed of light.
So I guess the question would be, who's right?
Well, no, the point is you're both right.
You're both right. That's right. Because the context is different.
Yeah. Yeah. So the statement is, you in your spaceship traveling, you are at rest in your rest frame and you measure your heart rate to be one thing.
Mm-hmm.
But for me, you're traveling towards me close to the speed of light. And this is the whole point, is spatio-temporal relationships are affected by your state of motion. So the fact that you're moving close to the speed of light is why when I go to measure the biological processes that are happening on your ship, they've slowed down.
Mm-hmm.
And that's a real effect. Like those muons literally make it to the surface of the Earth, whereas, you wouldn't think that they would. So these effects are real.
Liam asks, has Kant thoroughly corrupted physics? Is there any Aristotle left?
I don't really have a global view of the field of physics as such today. Kant has definitely affected it to a very large extent. On the other hand, there's a lot of discoveries, important discoveries that are being made. I gave a talk a couple of years ago at Ocon about a discovery in gravitational physics that was made with these gravitational wave detectors. So that was a huge achievement. They won the Nobel Prize for it. Important, valid, real discoveries continue to be made. even though there's a lot of philosophic corruption that's all over the place.
To what extent can we tell what these to what extent can the philosophy corrupt the discoveries to the point where we don't know if they're true?
Yeah, it's a good question. I mean, I think to some extent it has to do with what is the claim. Like you look at the popular science literature where they report on discoveries, and some of them they're just reporting on some paper that some guy wrote. That they're often that's what it is, where it's not like it's been validated. It's someone's theory or some idea, and they're putting it out there. But when it comes to a major discovery like these gravitational wave detections, this is a project of decades. I mean, I remember when I was a graduate student, they were starting to break ground building these detectors. And then in 2 decades later, they finally started making the first observations with them. And I mean, yeah, so I maybe I can't say across the board, but I know enough about this field to know that these are real discoveries.
Yep. Jason asked, are there easy to understand reasons why a futuristic camera could not bend light in such a way to take a picture of the past, a snapshot showing what happened hours, years, or decades ago?
Well, I'm not sure how bending, okay, first of all, there's a way in which when you're taking astronomical images, you are looking at the past. Because if you look at a distant star that's, a billion light years away, you're looking at light that left that star a billion years ago and coming to, so you are in effect, whatever you're looking at, you're looking on the past light cone of your current location. But I'm not sure. I don't really see a way that you would. So you're saying, I mean, I guess if you had, like a strong enough black hole in the vicinity, you could send out a light ray and it would circle around, and you could, if you had a strong enough gravitational field, you could bend it around and you would look at yourself from 5 minutes ago or whatever, but I don't know that that's what you're looking for.
Okay. Frank asked, do you think Dr. Michio Kaku is full of crap?
I don't really follow him. I think he's one of these science commentators who likes to do a lot of gee whiz. Like, on the one hand, I feel a certain sympathy for science journalists, because they confront the problem of hierarchy that we talked about all the time. They're trying to explain new discoveries, in gravitational physics or whatever, to people who don't have the context of knowledge to really understand what they're talking about. So they make all these analogies, like people talk about gravitational physics like it's like a trampoline. You've all seen these images of the curvature of space-time is like if you put a ball on a trampoline and it curves down. That's not what's actually going on.
Yeah.
But they have to try to find ways to explain these things. Now, I think some people kind of get off on the gee whiz factor. They like the fact that people can't really understand it, but it sounds cool, so I seem really smart. I don't know if that's what Michio Kaku is doing, but there are a lot of people who try to write popular books on science that I don't think succeed. I think I've read one of his books, but it was a long time ago, so I can't really say if he does that. A lot of that stuff is BS, I would say.
James Taylor asks, are there any physicists out there who are fans of Ayn Rand? Who do you think is the next Einstein?
I don't. I mean, there there are lots of physicists who are fans of Ayn Rand, but I don't know if there are any famous, prominent ones who've done major work, who are the next Einstein. I don't know.
Yep. Same as the last question, I guess. Are Sean Carroll and Michio Kaku hacks? Do you know Sean Carroll?
I mean, look, they're both working physicists, so I can't really comment on the value of their scientific work. I assume they both do as good work in whatever field they're working in as one can do. I have some of Sean Carroll's books. Again, I haven't read them yet. But I think the problem is whenever you are trying to write popular books about subjects that require an enormous context of knowledge, you confront the problem that we've been talking about through this whole episode, of which the problem of hierarchy. And you can work really hard to try to give enough context to make certain things plausible, but it's really hard to do. And I don't think the issue of hierarchy is well understood enough that science commentators or science journalists or people who are writing, scientists who are writing popular books on the subject even understand what the problem is that needs to be solved. So, yeah.
Hopper Campbell says, is Keith currently heading ARI's nuclear program for when we establish Galt's Gulch and need to defend ourselves? No,
No,
that's a whole separate secret department within ARI,
yeah.
not Keith's responsibility. Daniel, is the universe static or expanding? Have you read The Static Universe by Hilton Ratcliffe? What did you think?
I have not read it, and I haven't, I have no reason I'm just trying to think about the right way to put this. I have no reason to doubt the standard views in cosmology. There's a lot throughout the history of gravitational physics in particular. There are a lot of people who, have raised objections or doubts or questions about every aspect of it, from the so-called paradoxes of special relativity through questions in cosmology. From what I've seen, for the most part, those views tend to fall on the sort of crackpot side of the spectrum, not on the people who are really experts in cosmology and gravitational physics can usually pull those arguments apart pretty readily.
Mm-hmm.
But I haven't read it, so I can't speak to that one in particular.
Shazbot says, I was on my way to being the next Einstein, but then I got a haircut.
Congratulations.
All right. Apollo Zeus, what's your opinion of how gravity works? I think he told us that before, something about the fabric of time and space.
Yeah, well, let me just say this, that how gravity works is not a matter of opinion. It's a matter of scientific fact. And in order to understand it, you've got to understand everything that led from Newton up to Einstein's general relativity. So, again, you'll have to take my course on that if I ever get around to doing that.
All right. I like numbers says, is there only one right way to present the ideas?
That's a good question. I think it's relating to the issue of hierarchy. So there are definitely, so I think there's two parts to that. There definitely are cognitive options. There are some cases where you could present one thing first or another thing first, and there's a certain optionality to it. But there are other situations where the order is not optional. So so hierarchy doesn't mean that there's sort of one intrinsic order. And if you're teaching, if you want to get up to Newton's laws, you have to do this, and that's like this intrinsic order that you have to follow. as I said, there are options, but there are certain things that you have to, there are certain steps that have a certain order to them that you can't violate without falling into the problem of violating the principle of hierarchy. So just to give an example, in a typical physics class, they will give you Newton's law of gravity, and then they'll derive Kepler's laws of planetary motion from them. Now, historically, Kepler developed his laws before Newton was even born. And Newton couldn't have gotten to his law of universal gravitation without using the information that he got from Kepler's law. So in my course, we do Kepler first, and then we show how Newton used his third law to get to the law of gravity. So that's an example of, so the problem is that students who take a typical physics course, they have no idea where the law of gravity comes from. The teacher just wrote it on the board, and they can derive Kepler's laws from it, but they don't know how Kepler got his laws because he didn't have Newton's law of gravity. So it's all just a bunch of floating abstractions. You don't see how the knowledge was built up step by step.
Stephen asks, do you think John Galt's static electricity machine is possible?
I mean, my understanding is that there was a sort of invention from the early 19th or early 1900s or something that where they were trying to do something like that. I think it was something that Ayn Rand was drawing on, like a real thing. But I've never heard of it as a real invention, and I don't see, I don't have any reason to think that it could exist.
Yeah. What are the bridges between physics, chemistry, and biology, and especially if there is such a thing as living chemistry, a proposed gap between chemistry and biology?
I don't know enough about those fields. I mean, there is biochemistry. So what's the difference between biochemistry and living chemistry? I don't know.
Frank, I prefer steady state theory to Big Bang theory, but it is inconsistent with the properties of cosmic microwave background. Still, how can the universe be finite? We've talked about this. Yeah.
I think we talked about all the parts of that.
All right, Nicholas. Hello, it was nice to meet you last year. I found that physics degrees make for difficult employability versus engineering programming. I ended up doing nuclear masters to find work. Do you think that degrees need reform?
Oh, well, I mean, of all the, yeah, I mean, I don't think you have to take too close a look at the state of the universities today to know that they're in need of massive reform. And I think that's true in the sciences as much as it is in the humanities. So, but like the idea that, a university education could prepare someone for a career where they could be employed. It's like, if that were
What a concept.
Yeah, what a concept. Yeah. So yeah, I mean, I don't have specific suggestions for reform or directions, but I agree with the general idea.
Yep. I don't know if you want to answer this. I'll leave it up to you. What is your evaluation of David Harriman as a physicist? Actually, that's pretty easy to answer.
Well, I'll say this. I mean, I use The Logical Leap as a textbook in the course that was written, with the collaboration of Leonard Peikoff, and I think it's a really valuable work. I don't think the purpose of this podcast is to express opinions about people, so I'll just leave it at that.
Yeah, I try to tell them that. They still keep asking. Do black holes actually exist? Apollo Zeus asks.
Yeah.
Cool.
Yeah.
Daniel, I mean, yeah, good. You
No,
want to say
there's ample evidence by now that that they exist, that I mean these gravitational wave detectors have detected, the collisions of pairs of black holes, and there's a distinctive gravitational wave signature that is different from when two neutron stars collide, for instance. So there's no question about that.
Daniel asks, I've been trying to understand the different aspects in which concepts are open-ended. Could you explain that a bit? How does this relate to induction?
Well, I mean, the idea of concepts being open-ended is just that when you form a concept, the units that are subsumed by that concept are potentially unlimited. So Ayn Rand gives the example in Introduction to Objectivist Epistemology, gives the example of forming the concept of a table. I mean, when you form the concept of a table, it's on the basis of the very limited number of tables that you've encountered as a child, your dining room table, your kitchen table, the table at your friend's house, right? You form the concept of table, but once you have the concept, and you view each table as a unit of the concept stands for any table that you encounter in the future, any table that's existed in the past, any table that will exist in the future. Like that's what it means to say that it's unlimited. So the way that's relevant to induction is the act of forming a concept is the act of forming a generalization, having a perspective on an aspect of reality that goes from the particular to the general. So you go from the few tables that you observe to this potentially unlimited set of tables. So it's that process that underwrites the ability to form generalizations, to form inductive generalizations. I mean, that's my understanding of the theory.
Yep.
But I should say, I mean, this, I'm not I should have said this at the beginning. I'm not, a philosopher. I'm not an epistemologist. I'm just a humble guy with a PhD in physics who's teaching a course on the history of science for ARU. So.
John says, would it be appropriate to teach physics students physics and calculus together in the same course?
I mean, in the right context, sure. I think actually it would be, I mean, what could be better is to teach calculus in a historical way, like to look at the historical development of calculus, because that would you would see what gave rise to the development of the calculus in itself. So yeah.
But I think the real question is, who invented the calculus first? Was it Leibniz or Newton?
I think there's evidence is that Newton did it first,
I
but
think
he
so.
didn't. But he didn't publish it. So
They did do it independently.
Yeah.
So yeah.
Yeah, I haven't looked into that whole dispute, but I think they independently came up with it, and Leibniz's notation was better, and so that won out eventually.
That's right. It was this annotation was, that's right. That's what we use today is the Leibniz notation. I told you about these novels I read.
Oh yeah.
Yeah, that are kind of centered around the whole dispute. They're like 8 novels or something. There were 8 in a series of 8 of them, and
I think I have them in an Amazon cart, and I've just never pushed the button.
they were like really cool until the last one where it got really weird and unjustifiably just off, went off in some tangent. But generally, they were pretty cool because you learned a lot about that period in history.
Yeah, I should read those.
Papa Campbell says, do wormholes exist? Do they come out of Einstein's field equations like black holes do?
Well, theoretically they can come out of Einstein's equations, but I don't believe there's any evidence that like in order to construct them, you have to have a very specialized, setup. So black holes form just can conform just from the collapse of ordinary stars. But wormholes, in order to set those up, they have to be very specially constructed. So yeah, so I don't think there's any evidence. There's no reason to think that wormholes exist. Yeah.
Jacob says best value for the last chat with Brian. Thanks, Jacob. Paulo Zeus, will the big crunch happen? Is that the collapse of the universe?
Yeah. I don't know enough about cosmology to.
If it does, it's beyond our lifetime. So
Yeah.
a little.
I do. I do constantly think about and confront the second law of thermodynamics. Every time a plate chips or a glass breaks, I go, oh, what can you do? It's the inevitable tendency toward chaos and disorder of the universe. So
that's a good excuse when you broke the glass or you broke or you chipped it. I'm sure that works really well. All right, Apollo's this is the last question, actually. All right. Apollo just says, I heard a sugar cube size sample of a neutron star is so dense and heavy it would, if dropped, make a hole in the earth. Your thoughts?
Yeah, probably true. What I remember from my grad school days is you would measure it in tons per teaspoon, the neutron star matter.
Tons per teaspoon. Wow.
Yeah. You have an object, that's essentially around the mass of our sun, but it's condensed down to like the size of a large city, like Chicago or New York or something like that. So yeah. This is dense stuff we're talking about here.
All right. Thanks, Keith.
Okay, this was fun.
Yeah, it is fun. Thanks, guys. Thanks for all the questions. This was great. And we'll have Keith back so you can stock up on new questions. I know some people thought they didn't ask the question quite right, so they want to take another shot at you. So we'll do that next time. I will see you guys tomorrow, 2 p.m. for our usual show. I'll see Keith at Ocon. Well, I'll see you on video in a couple of weeks. Bye, everybody. Have a great night.